Okay, morning. This is Vector Calculus, lecture 14. And what we are studying are functions of several variables. So you could have a function of two variables, x and y, and if you have such a function, it might be defined on some domain of the xy plane, and the graph is a surface in three-dimensional space. So we think of it something like this, that here is the xy plane, and you have some function, and sitting over it is the surface. This is a point here. We'll have coordinates. If this is the point xy 0 in the xy plane, this point will have coordinates xy, and the third coordinate is f of xy. So just the way you think of the graph of a function of one variable as a curve in two-dimensional space, you think of the graph of a function of two variables as a surface in three-dimensional space. Now, we also look at functions of three variables, x, y, and z, and a graph, if you could draw it, would be something in four-dimensional space, and we have the human brain is not able to see surfaces or graphs in three-dimensional space, so we don't deal with that. We don't worry about trying to find these things. When we're trying to understand surfaces, we look at level curves in the xy plane. So you consider for a fixed value c, the points all xy such that f of xy is equal to c. This is some set in the plane. So suppose we had the function f of xy equals x squared plus y squared. So the level curve f of xy equal 1, this is all points where x squared plus y squared equals 1. That's the surface It's the circle of radius 1. You looked at the level curve, f of xy equals 16. That's all points where x squared plus y squared equals 16. That's the circle of radius 4. So for this particular function, the level curves are circles centered at the origin. This is actually not too hard to picture. This is really a paraboloid. It looks like, if you looked at the surface, it's a parabola rotated around the z-axis, what we call a paraboloid. And the best way to understand what is going on is to read and reread and reread the text and study the pictures there, which are drawn very carefully. All right. Any questions? Just interrupt me, because this is all review of what we've been talking about. So let's say we have a function of two variables, z equal f of x, y. You know, for a function of one variable, we're interested in the rate of change of the function, and it's measured by the derivative, df dx. Right? And we'd also, and what this means is, if you have your function, and this is its graph, y equals f of x, you want to know as you go from this point to this point, say, how much the function changes. And the instantaneous rate, and that's just the slope of the secant line. And the instantaneous rate of change, which is the slope of the tangent line, is the derivative. It's how much the function, how rapidly or how slowly and in what direction, positive or negative, the value of the function is changing at some particular point, say A. For a function of two variables, it's more subtle because you have the surface, this is the graph of this, the graph of this function is a surface, and you might want to know at some point, here's some point x, y, 0, and on the graph, this is the point x, y, f of x, y. How rapidly are things changing here? And the answer is it depends on what direction you go in, because it might be changing at one speed if you go in this way along the curve, or at a different speed if you go in a different direction along the curve. So for functions of 2 or 3 variables, we need what are called the directional derivatives. Derivatives in a fixed direction u, say u1, u2, where we take u is a unit vector. It's a non-zero vector of length 1. And the two simplest cases in these starting cases are when you go in the horizontal direction, 1, 0, or when you go in, so this is in the x direction, or when u is 0, 1, which means you're going in the y direction. And in this case, the directional derivatives are called the partial derivatives of the function. So we have the function f, the partial derivative of f with respect to x at some point x, y, or sometimes one writes f with a little subscript x at x, y. This means in the xy plane, here's x, y. You want to move a certain amount horizontally. You look at x and x plus h. And you want to know what is the difference in the values of the functions between f of x and between x and x plus h. That's f of x plus h minus f of x. That's sort of the average rate of change will be that difference divided by h. And then, but this is comma y, x comma y. And you take the limit as h goes to 0. And the partial derivative of f with respect to y, now you're going in the vertical direction. So from xy to xy plus h. So this is, you look at f of x, y plus h minus f of y divided by h. Take the limit of that as h goes to 0. And these give you rates of change in the x and the y directions for your function. And they're very nice pictures in the book to illustrate this. And again, it's very good if you have the book with you during class, but you should certainly study this yourself a lot at home. So for example, if f of x, y is the function x cosine of x, y, the partial of f with respect to x is like y is a constant. And you differentiate this with respect to x, you would use the product rule. This is the derivative of x, which is 1 times the cosine of xy, plus x times the derivative of the cosine of xy with respect to y, which is minus the sine of xy times y. So you get this partial derivative of f with respect to x is cosine xy minus xy sine of xy. If you take the partial derivative of f with respect to y, x is like a constant. The derivative of cosine of xy with respect to y is minus the sine of xy times the derivative of xy with respect to y, which is another x. So you get minus x squared sine of xy. And I hope you will do a lot of problems because you need to develop this skill. There's no difference if you look at a function of 3 variables. So suppose you have the function, and it doesn't matter what letters you use, x, y, z, u, v, w, a letter is a letter. Suppose the function is f of u, v, w is u over v plus w. So now we can take partial derivatives with respect to u, with respect to v, and with respect to w. If we differentiate this with respect to u, this is 1 over v plus w times u. That's 1 over v plus w, which is like a constant, times the derivative of u with respect to u, which is 1. So the partial of f with respect to u is 1 over v plus w. The partial derivative of u with respect to v, so this is u times the derivative of 1 over v plus w. This is like u times v plus w to the minus 1. So by the ordinary chain rule from Calc 1, this is minus v plus w to the minus 2 times the derivative of v plus w with respect to v, which is 1. So this is minus u over v plus w squared. And if we differentiate this with respect to w, again, this is u, and the derivative of v plus w to the power minus 1 is minus v plus w to the power minus 2. So this is again minus u over v plus w squared. Any questions about this? Okay, now, if you recall the chain rule from calculus 1, if you have a function y, which is a function of x, and x is some function of t, then you have the composite function. Y equals f of x of t. And the chain rule tells us that dy dt is the derivative of y, or f, with respect to x times dx dt. Right? That's the chain rule from Calc 1. And in Calc 3, or vector calculus, we have also a chain rule. So suppose, let's say that z is a function of x and y, and x is a function of t, and y is a function of t. So z becomes a function of t. This is z of f of x of t, y of t. So this is the chain rule, which you have to know. It says if you differentiate this function with respect to t, This is the partial derivative of the function with respect to x times dx dt, plus the partial derivative of the function z with respect to y, dy dt. So this is the first new thing that we're doing today. I'll give it a star because it's so important. That's the chain rule. So here's an example. Suppose we have the function z equal x squared minus 3y squared plus 20, but x and y are functions of t. X is 2 cosine t, and y is 2 sine t. So the composite function is a function of t, and to work out its derivative by the chain rule, dz dt is the partial of z with respect to x. If you differentiate this with respect to x, you just get 2x times dx dt, which is minus 2 sine t, plus the partial of z with respect to y, which is minus 6y, times dy dt, which is 2 cosine t. So we get minus 4x sine t minus 12y cosine t. Right? That's the chain rule. Let me do a couple of examples because it's important to see this done often and then to do a lot of examples yourself. Suppose we have the function z equal to x plus 2y to the 10th power, and x is sine squared t, and y 3t to the 4th, 3t plus 4 to the 5th. So the composite function is a function of t. dz dt is the partial of z with respect to x, dx dt, plus the partial derivative of z with respect to y, dy dt. If I differentiate this with respect to x, I get 10 x plus 2y to the 9th. If I differentiate x with respect to t, I get 2 sine t cosine t, plus the partial derivative of z with respect to y. When I differentiate this with respect to y, I get 10 z plus 2y to the 9th, sorry, x plus 2y to the 9th, plus the derivative of x plus 2y with respect to y, which is 2, times dy dt. If I differentiate this with respect to t, I get 5, 3t plus 4 to the 4th, times the derivative of 3t plus 4 with respect to t, which is 3. So I have 20 x plus 2y to the 9th sine t cosine t. Here I have 10 times 2, which is 20, times 5, which is 100, times 3, this is plus 300. X plus 2y to the 9th, 3t plus 4 to the 4th. I can factor out x plus 2y to the 9th. I get 20 sine t cosine t plus 300, 3t plus 4 to the 4th. And then I can put in what x and y are in terms of t. This is sine squared t plus 2, 3t plus 4 to the 5th times this expression. So now everything is a function of t. Now, I should emphasize or should state that all the functions we look at will have continuous partial derivatives, and the chain rule works for them. The chain rule does not necessarily work for functions that have partial derivatives that might be discontinuous. Okay, now let's go back to finding derivatives, directional derivatives of a function of several variables. So we have some function z equal f of x, y. And this is the graph. It's the surface. If you take a point on that surface, and so this is x, y, f of x, y, that's sitting over the point x, y, 0 in the xy plane. Suppose we want to go in a certain direction u with coordinates u1, u2. So this xy plus u is x plus u1, y plus u2. And there's a point over that in the xy plane. And this line, its image in the surface is this curve. And we want to know the directional derivative in the direction of u. So the derivative of z equal f of x, y in the direction of u, which is a unit vector. That is, the length of u is 1. How will we define that? We would say, well, if we go a certain distance h in the direction u, hu is the vector hu1, hu2. So xy plus hu is the vector x plus hu1, y plus hu2. Or at a point AB, just to use the same notation that the book is using, if we have some point AB and we look at where it sits on the surface, I'm interested in the rate of change. If I look at f of a plus hu1, b plus hu2, minus f of b, so that's the change as you go h units in the direction of the vector u, divide it by h, and I take the limit as h goes to 0, this limit if it exists, is the directional derivative, then we write capital D for directional derivative in the direction u of the function f at the point AB. So let me just emphasize this by writing it down again. The derivative of the function z equal f of x, y at the point AB in the direction of the vector u equal u1, u2, you take f of a plus hu1, comma, b plus hu2, minus f of ab divided by h. Take the limit of that as h goes to 0, and that's the directional derivative of f at ab in the direction of u. So this is the official definition, which is important to know, but I'm not going to ask you to memorize it and write it down. So in the xy plane, if this is the vector u, and you're at some point AB, the line through AB parallel to u is parametrized by the coordinates. Let me use s as the variable. This is a plus s u1, b plus s u2. And if I look at f along this line, so I have f of so at a point on this line, let me think of this as a function of s. G of s is f of a plus s u1, b plus s u2. So when s is 0, you're at the point AB, and as s varies, you're moving along this line in the positive or negative direction. So this describes the value of the function along this line L. This is the line through the point AB in the direction of the vector u. So it's like we have f is a function of x of s and y of s, where x of s is a plus su1, y of s is b plus su2. And the derivative of the function f at the point AB in the direction u is exactly the derivative of g at s equals 0. It's the rate of change along this line. And if I apply the chain rule to a function of two variables, this is the partial of f with respect to x, partial x with respect to s, plus partial of f with respect to y, partial y with respect to s. I mean, you don't have to know this derivation, but it's not good to see, and you have to know the result. This is the partial of f with respect to x. The partial of x with respect to s is u1. And this is the partial of f with respect to y. Partial of y with respect to s is u2. So this is exactly the same, and this is evaluated at the point AB. So this is exactly the same as taking the vector partial of f with respect to x at AB, comma, partial of f with respect to y at AB, dot product with u1, u2. And this is, in fact, the directional derivative of f in the direction u, which tells us a very important fact, which makes calculus of vector calculus a lot easier. If you can calculate the partial derivatives of a function with respect to x and y, you can get from that right away the directional derivative of the function f in any direction u that you're interested in. And in fact, this vector, we'll use a shorthand for that. It's an upside down delta or upside down triangle, delta f at AB. And this is called the gradient of z equal f of x, y at the point AB. So the directional derivative of a function in the direction u is the gradient of f at the point dot product with the vector u. So this is a very concise formula for the directional derivative. Of course, you have to know what the gradient is, but the gradient is something we're going to be using over and over and over and over again. So you will definitely know what that is. This gradient is very important. Not just important, it's very important. Important. Good to spell the word properly. Very important. The gradient of a function at a point is the vector whose coordinates are the partial derivatives of the function at that point in x and y or x, y, and z, depending on whether you're using two variables or in the case of three variables. Let's do a couple more examples. Suppose we have the function z equal f of x, y, which is a fourth x squared plus 2y squared plus 2, and we take the point AB to be 3, 2, and we take the direction u, it has to be a unit vector, so that'd be the unit vector with coordinates 1 over root 2, 1 over root 2. So that's just a unit vector in this direction. That's u. And I want to compute the directional derivative of f in the direction u at the point 3, 2. So I have to compute the partial derivatives. The partial derivative of f with respect to x is 1/4 2x, or x over 2. So the partial derivative of f with respect to x at the point 3, 2 is 3/2. The partial derivative of f with respect to y is 1/4 2 times 2y is y. So the partial derivative of f with respect to y at the point 3, 2 is 2. So du, the partial derivative is the partial of f with respect to x at 3, 2 times the first coordinate of this function plus the partial of f with respect to y at 3, 2 times the second coordinate of the direction, 1 over root 2. So this is 3 halves times 1 over root 2, 3 over 2 root 2, plus partial of f with respect to y is 2, 2 times 1 over root 2. Which is what? This is 3 root 2 over 4 plus root 2, which is 4 root 2 over 4. So if I did this correctly, but maybe I didn't. Let's see. If this is z, the partial of f with respect to x is x over 2. So at 3 halves, at x equals 3, this is 3 halves. Partial of f with respect to y is y, so at 3 halves, that's equal to 2. So I get 3 halves times 1 over root 2 plus 2 times 1 over root 2. So this is 7 over 2 root 2. That's the partial derivative. So that's the directional derivative in the direction of the vector u. If I take a different direction, the direction v equal to 1/2 minus root 3 over 2. So that's the vector which looks like that. This is v. The directional derivative of f at the point 3, 2 in the direction of v will be the partial of f with respect to x times the first coordinate of v plus the partial of f with respect to y times the second coordinate of the direction v. So this is 3/4 minus root 3, whatever number that turns out to be. Recall that the gradient of f, which is this upside down delta times f, is the partial of f with respect to x, partial of f with respect to y. In a function of 2 variables and in a function of 3 variables, you would have partial f with respect to x, partial f with respect to y, partial f with respect to z. So if you have the function f of x, y is 3 minus x squared over 10 plus xy squared over 10, the partial of f with respect to x is minus 2x over 10, or minus x over 5. Partial of f with respect to y is x times 2y over 10, which is xy over 5. So the gradient of f at any point xy is minus x over 5, xy over 5. Oops, I'm sorry, I made a mistake. The partial of f with respect to y, this is 0, 0, this is xy over 5. Partial of f with respect to x, differentiate this with respect to x, I get 0. Differentiate this with respect to x, I get minus x over 5. Differentiate this with respect to x, I get plus y squared over 10. So the gradient of f at xy is minus x over 5 plus y squared over 10, comma, xy over 5. So if I want the gradient, for example, at the point 3 minus 1, when x is 3 and y is minus 1, this is minus 3/5 plus 1/10, which is minus 1/2. And when y is minus 1, this, and x is 3, this is minus 3/5. So the gradient of this function f at the point 3 minus 1 is minus 1/2 minus 3/5. And if I take the unit vector u equal to 1 over root 2 minus 1 over root 2, then the directional derivative of f in the direction u at the point 3 minus 1 is the gradient of f at 3 minus 1 dot product with u. That's the gradient of f at 3 minus 1 is minus 1/2 minus 3/5 dot product with 1 over root 2 minus 1 over root 2. So this is equal to minus 1 over 2 root 2 plus 3 over 5 root 2. So if I put this over a common denominator of 10 root 2, this is 6 minus 5 is 1. So this directional derivative is 1 over 10 root 2. Now, very often, when you're looking at some surface, you have a point on the surface. This is the graph of the function z equals f of xy, and this is the value of the function over the point AB. You want to know in what direction does the function increase most rapidly. To give a really simple example, suppose your function looks like this, your surface. If you take a point right here and you go in this direction, the function doesn't change. The rate of increase is 0. But if you go in this direction, it increases the fastest. There are different directions in which the function increases rapidly and other directions in which it increases slowly. So the problem is to find the direction u such that the directional derivative of the function f at the point A, B in the direction u is the maximum, is largest. Well, we recall the directional derivative of f at AB in the direction of u is the gradient of f at AB dot product with the vector u. And we want this to be as large as possible. Well, the dot product of two vectors is the length of each vector times the cosine of the angle between them. But u is a unit vector, so the length of this is 1. So this is the gradient of f at AB times the cosine of theta. Now, cosine of theta varies from -1 to 1. From 0 to 2 pi, cosine looks like that. And you have a maximum at theta equals 0. So theta equals 0, which means that the gradient of f at AB is parallel to u. Right? You have two vectors. This is the angle between them. That angle is 0 when the two vectors are pointing in exactly the same direction. So the maximum value of the directional derivative of a function at a point is when the direction is the direction of the gradient. So, and the rate of change is, so when theta equals 0, the value of the directional derivative of f at AB is the magnitude of the gradient vector. So the gradient tells you in what direction a function of two variables or three variables is increasing most rapidly, and what that maximum rate of growth is. And when theta is pi over 2, cosine theta is 0, and the directional derivative of f at AB in the direction u is 0. Cosine theta equals 0 means here's the gradient. Cosine is 0 at the angle pi over 2. So when you go in a direction perpendicular to or orthogonal to the gradient, the rate of increase is 0. So if you look at the book, which I encourage you to do, at the bottom of page 965, section 15.5, it says that f be differentiable at AB with the gradient non-zero. The function f has its maximum rate of increase at AB in the direction of the gradient. The rate of change in this direction is the length or the magnitude of the gradient vector, and the directional derivative is 0 in any direction orthogonal to or normal to or perpendicular to the gradient. The gradient is really, 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 really important. You have to spend a lot of time studying the gradient, calculating gradients, and working problems with gradients. Let me do a few more examples. And I'm going to really spend the rest of this period just doing problems with gradients. So suppose we have the function z, it's a function of x and y, and it's 4 plus x squared plus 3y squared. You notice that f of 0, 0 is equal to 4. So at 0, 0, the value of the function is 0. And this is a paraboloid. This is a function whose surface, whose graph, is the surface of this cone-shaped figure. And if you compute f of 2 minus a half. If you let x equal 2 and y equal minus a half, you get 4 plus 2 squared plus 3 times minus a half squared. This is 4 plus 4 is 8, minus 3/4. Sorry, 4 plus 4 is, 4 plus 4 is 8, which is 8 is 32 over 4, minus 3 over 4. Oh, I'm sorry. X equal 4. When x is 4, this is 4. So this is 4 plus 2 squared plus 3 times minus a half squared. Oh, sorry. So this is plus. This is 4 plus 4 plus 3/4. This is 8, which is 32 plus 3 is 35 over 4. So on the parabola, there is a point P whose coordinates are x equal 2, y equals minus a half, z is 35 over 4. So that's a point on this paraboloid. And we want to know, in what direction do you have to move to go up on the surface as fast as possible? Right, so find the direction and the rate of maximum increase. So if f of xy is 4 plus x squared plus 3y squared, the partial derivative of f with respect to x is 2x. So the partial of f with respect to x, when x is equal to 2 and y is minus a half, is 2 times 2, or is 4. Partial of f with respect to y is 6y. So the partial of f with respect to y at 2 minus a half is 6 times minus a half is minus 3. So the gradient of f at the point 2 minus a half is the partial of f with respect to x, that's 4. Partial of f with respect to y, it's minus 3. So that's the gradient of f at minus 1/2. So the direction of maximum increase is a unit vector in this direction. What is the length of this vector? The length of the gradient of f at the point 2 minus a half, the magnitude, is the square root of 4 squared plus minus 3 squared. That's 16 plus 9 is 25, square root is 5. So the direction of maximum increase, you take a unit vector in that direction, that's 1/5 4 minus 3, or 4/5 minus 3/5, and the maximum rate is equal to 5. So this is the direction of steepest ascent going up. The direction of steepest descent is the negative of this, is minus u. So that's minus 4/5 plus 3/5. Let me just pause for 1 second. Yeah. Any questions about this? This is really fundamental for us. So there's a connection between the gradient and level curves. So let's review level curves again for a moment. So the directional derivative f sub u, or d sub u of f at AB is 0 in any direction orthogonal, which is the same as perpendicular, to the level curve, sorry, in any direction orthogonal or perpendicular to the gradient of f at the point AB. So the maximum directional derivative of a function is in the direction of the gradient. That's where the function is increasing most rapidly. The function is decreasing most rapidly in the direction opposite to the gradient. And the directional derivative is 0 when you are going in a direction perpendicular to the gradient. Now, suppose we look at the level curve. F of xy equals to some value z naught. So in the xy plane, this is some curve and at any point on this curve, at every point on this curve, the value of the function is z naught. So as you move along this curve, the value of the function doesn't change. If you think of this as on your surface, on this level curve, somehow the function isn't increasing. So that suggests that on this level curve, if you take the directional derivative on this level curve, that is the tangent to the curve at some point, the function is not changing, so this tangent should be 0. Right? So let's see, and I want to find a better way to say this. So you have a level curve, f of xy equals z naught. That's some curve in the plane. And at some point, AB, there's a tangent to this curve. And this tangent should be perpendicular to the gradient of the function at AB. So this is stated as a theorem in the text that given a function differentiable at AB, the line tangent to the curve of f at AB is orthogonal to the gradient, provided this gradient, of course, is not the 0 vector. So Let me try to do an example first, and then I want to prove this fact. So this is an example from the text. This is example 6 on page 967. Suppose we have the function z equals f of x, y is the square root of 1 plus 2x squared plus y squared. So this kind of function has a name, but the name doesn't really matter to us. This is an example of what is called a hyperboloid, but there's no reason for you to know that or remember that. But this is a function of two variables. It's defined for all x and y, because for all x and y, what's under the square root sign is not only positive, it's at least 1. It's 1 plus something non-negative. So this function is defined everywhere. What is f at the point 1, 1? When x is 1 and y is 1, you get the square root of 1 plus 2 times 1 squared plus 1 squared. That's the square root of 1 plus 2 plus 1, which is the square root of 4, which is 2. So the level curve, f of x, y equal 2, passes through the point 1, 1 on the xy plane. In fact, let's just see if we can graph this. I mean, if you know Maple, of course, Maple can do everything for you, all these functions, all these curves. So we have the function z equals f of x, y is the square root of 1 plus 2x squared plus y squared. At the point 1, 1, the value of the function is 2. So if we look at the level curve, f of x, y equals 2, that's the same as saying it's all points x and y where 1 plus 2x squared plus y squared equals 2. If you square both sides, you get 4 equals 1 plus 2x squared plus y squared, or 2x squared plus y squared equals 3. What is the graph of this? Well, you may or may not have learned, though you should have somewhere, that this is an ellipse. This is the same as 2/3 x squared plus 1/3 y squared equals 1. Or another way of writing this is that x squared over 3 halves, or x over the square root of 3 halves squared plus y squared over the square root of 3 squared equals 1. So this is an ellipse where the major axis is root 3 over 2, and the minor axis is root 3. So this level curve is this ellipse in the plane. And let's see, let me just double check something, because the point 1, 1 satisfies this. This is x squared, 2/3 x squared over 3 halves, y squared over square root of 3, yeah. So root 3 over 2, yeah, okay. So this is some ellipse. This is root 3 minus root 3. Root 3 halves minus root 3 halves. And the point 1, 1 lies somewhere on this ellipse. So this level curve for this function is this ellipse. Let me just repeat that again or go through it again, because this is all kind of pre-calculus, if you like. But you have the function f of x, y is the square root of 1 plus 2x squared plus y squared. If you let x and y equal 1, the value of the function is 2. So if you look at all points on this, all points x, y, for which f of x, y equal 2, that is the definition of a level curve. The level curve, f of x, y equal 2, it's all points where square root of 1 plus 2x squared plus y squared equals 2. If you square both sides, you get 4 equals 1 plus 2x squared plus y squared, or 2x squared plus y squared equals 3. Or you can rewrite that in the classical form for an ellipse, x squared over a squared plus y squared over b squared equals 1. That's the ellipse where x goes from minus a to a, and y goes from minus b to b. So this is something you're supposed to have learned before vector calculus. And so this is the ellipse where a is root 3 over 2 and b is root 3. And the point 1, 1 lies on that ellipse. So that is the level curve for this function. What is the gradient of f at the point 1, 1? So the gradient of f, this is f. When I differentiate this with respect to x, I have to remember calculus. This is 1 over 2 times the square root of 1 plus 2x squared plus y squared times the derivative of this with respect to x, which is 4x, comma 1 over 2 times the square root of 1 plus 2x squared plus y squared times the derivative of this with respect to y, which is 2y. So the gradient of f at the point 1, 1 is 4 over 2 times 2, comma 2 over 2 times 2, excuse me. So this is 1/2. No. So what I want to show is that if I had the tangent line to my level curve at this point, the gradient is perpendicular to it. This is the gradient of f at the point 1, 1, and that's my, so I need to find the tangent line to the curve at this point. So I can use, so I want to find the tangent line to the ellipse at the point 1, 1. So the ellipse is given by 2x squared plus y squared equals 3. I want to find dy dx. I can either solve for y and differentiate. And differentiate, I can use implicit differentiation, which you learned in calculus. If I differentiate this with respect to x, I get 2 times 2x plus 2y times dy dx equals 0. So dy dx is minus 4x over 2y is minus 2x over y. So dy dx at the point 1, 1 is minus 2. So the derivative at this point is minus 2. So the tangent line at the point 1, 1 is y equals minus 2 x minus 1 plus 1. You have to remember this is fundamental in Calc 1, how to find the tangent to a curve at a point. It's minus the slope x minus 1 plus 1. This is minus 2x plus 3. So that's the tangent line. And let me just draw a picture of this. Here we have the ellipse. Here's the point 1, 1. The tangent line to this point is y equals minus 2x plus 3. What is the direction of the tangent line? Well, let's just find the gradient of f at 1, 1 is one minus a half. So this vector 1 minus a half, this is a vector whose, if I take, sorry, is that the gradient? No, 1 plus a half. So a line through the point 1, 1 in the direction of 1 a half will have slope equal to a half. So the line here has slope 1 half. The tangent line has slope minus 2. A half times minus 2 is minus 1. So you learned in pre-calculus, or I hope, that two lines are perpendicular if the product of their slopes is minus 1. And that's the situation here. Let me again review this or go through this again, just because there's a lot of calculus that you have to know to solve these problems. And a lot of the calculus is from Calc 1 and Calc 2, which you may have forgotten, but somehow you need to get back up to speed on. So we started with the function. Let me actually start it on a whole fresh piece of paper. Z equal f of x, y is the function square root of 1 minus 1 plus 2x squared plus y squared. F at the point 1, 1 is 2. So we're interested in the level curve, f of x, y, which is the square root of 1 plus 2x squared plus y squared equals 2. What is that curve? If I square both sides, I get 1 plus 2x squared plus y squared equals 4, or 2x squared plus y squared equals 3. If I write that as this is an ellipse, in the usual form in which you write an ellipse, this is x squared over 3 halves plus y squared over 3 equals 1. So this is an ellipse where this is root 3 minus root 3, root 3 over 2 minus root 3 over 2. And on this ellipse is the point 1, 1. And I want to show that the tangent line to the ellipse at this point is perpendicular to the gradient at this point. So how do I find the tangent line? I want to compute the tangent line to the ellipse at the point 1, 1. So I must find if I think of y as a function of x, dy dx at the point 1, 1. And I can do it most quickly by using implicit differentiation, using this equation for the ellipse. If I differentiate with respect to x, I get 2 times the derivative of x squared, which is 2x. The derivative of y squared with respect to y is 2y dy dx equals the derivative of a constant 3, which is 0. So dy dx this is 4x, it's minus 4x over 2y, or minus 2x over y. So dy dx at the point 1, 1 is minus 2. So I want the line through the point 1, 1 with slope negative 2. So by the point slope formula, the tangent line is y equals minus 2x minus 1 plus 1 is minus 2x plus 3. This is the tangent line. Y equals minus 2x plus 3. The slope is minus 2. What about the gradient of f? The gradient of f at xy, you take the partial derivatives of f with respect to x and with respect to y. So the partial derivative of f with respect to x is, I'm differentiating this with respect to x. I get 1 over 1/2 square root of 1 plus 2x squared plus y squared times the derivative of this under the square root sign with respect to x is 4x. And the derivative of this with respect to y, I get 2 square root of 1 plus 2x squared plus y squared. Derivative with respect to y is 2y. So the gradient of f at the point 1, 1, this is 2, so I get 4 times 1 over 2 times 2, comma, 2 times 1 over 2 times 2. This is 1, 1/2. So the gradient is this vector. That's the gradient of f at 1, 1. It's the vector 1, 1/2. Any line in this direction will have slope 1/2. -2 times 1/2 is -1. So the line through this point in the direction of the gradient has slope 1/2 is perpendicular to any line with slope -2, because the product is -1. And this is example 4 on page 966 with much better pictures drawn. And I would strongly encourage you to spend a lot of time, if you can, studying this section on the gradient. We still have a little bit more to do. Plus we have to look at the gradient for functions of 3 variables as well as functions of 2 variables. But we use directional derivatives and gradients over and over and over and over again in math, in this math, whatever it is, 226. And a large part of the second midterm, which isn't that far away, if you look at the schedule, will have to do with the directional derivatives. If you have questions, again, I have a lot of problem sessions on Zoom that are underutilized, and I encourage you just to log on and ask questions or ask for help with homework problems, anything of that sort. I have 3 more. I have 3 more sessions this week. This evening at 7, Thursday evening at 7, Friday afternoon at 4:30, and you shouldn't hesitate to log on and ask questions or ask for homework help, or help with just understanding the theoretical material. Okay. If there are not any questions, I would say enjoy the rest of the day and enjoy the weekend, and we'll be back Monday morning. Bye all.
Have a good one, Professor.
Thank you.